Okay, we're going to continue on here, chapter 13. We got into acids and bases last time. So as we talked about, an acid is really something that has the ability to produce free H plus ions in solution. Remember as well as we talked about that H plus and H3O plus are essentially sort of interchangeable here in acid-base chemistry. They basically represent sort of the acid part of the solution. And again, an acid is something that has the ability to produce free H plus ions. Again, not attached to anything. The amount of H plus in that solution determines, as we talked about a little bit, as to whether it's going to be acidic or basic or maybe neutral. Bases, on the other hand, are substances that can produce hydroxide, and it's the same idea there. Basically, free hydroxide ions floating around in the solution, and that's going to be something that is a base. That's sort of the general definition of acid and bases is the production of H plus or OH minus. A more sort of generic definition of an acid and base is the Bronsted-Lowry definition that we talked about there at the end. And in a Bronsted-Lowry acid, it's a proton donor. And again, an H plus is also sometimes referred to as a proton in acid-base chemistry. And a base is a proton acceptor. A result of that is if we have something like this, which is say an acid, and we react it with a base, again, we can use water in this case as a base. Here, we're going to send the H plus over. As we talked about, again, remember that it is not just the H, but the plus that comes over as well. And we could have something like H3O plus and A minus in this case. And what Bronsted-Lowry does is it creates partners on the other side of the arrow. So where you have your acid, its partner on the other side is its conjugate base. And where you have your base, its partner on the other side is the conjugate acid. And remember that your sort of acid and bases are found on the left-hand side of the arrow. Your conjugate acid bases on the right-hand side of the arrow. And again, this is the only difference that there can be in order for those guys to be related to each other is just that one H plus. Again, if you have something like we saw it there at the end that has the ability to give away 2 hydrogens or even 3 hydrogens, they do come off one at a time. So I think we had the H2SO4 and the SO4 2 minus. Again, these are not considered partners because there is sort of an intermediate in between those two guys that happens as this guy loses its hydrogen. And then this guy would lose a hydrogen and make a little SO4 2 minus. So it's a stepwise fashion, as we talked about there at the end, that hydrogens come off. They don't just all just pop off at once. I actually guess, as we'll see a little bit later on in this chapter as well, progressively harder to remove hydrogens after you remove one of them. And again, that is why, as we talked about, this guy and this guy are partners. This guy here and this guy here are partners. But again, kind of jumping a step there, they are not partners in between. Any questions on any of that there? All right, then let us continue on here. What would be the formula of the conjugate acid in this case? So why don't you take a moment there? You got some options. All right, so let's take a look. Hopefully, again, you understand that really this is what you're looking at. And really the question a lot of people have is, should I put it on or take it off the H plus? So if you just understand what we just talked about there, it could help you maybe figure out what you should do. So we have an acid and a base, then we have some conjugate acid and conjugate base on the right-hand side. acid to the conjugate base, base to the conjugate acid. So in this particular case, if we're looking for the formula of the conjugate acid, that is where we want to end up, which means if we go backwards, that tells us that what we are looking at is a base, and all we have to do is just do the Bronsted-Lowry definition of a base, which means it should accept the H plus. So in this case, we should put the H plus on. So we'll have the exact same guy here, and you could just slap in a H, and remember the plus as well is important. So it looks like maybe 2 would be a winner there. Yeah. Any questions on that there? All right, so why don't you try this one here? Let's do HCO3 minus. Why don't you write the conjugate acid, and why don't you do the conjugate base for it as well, starting with that.
It's already a conjugate acid and then it's becoming a base.
No, you're actually looking to find the conjugate conjugate acid, and he's telling you they were actually nice in this question. Actually told you that these guys are bases. That you're actually starting with this guy as a base, but most questions won't have that part. Most questions will just ask you to find the conjugate acid. So that's really what it's asking you for, is what's the conjugate acid in this case. They're actually giving you a nice piece of information that that was actually a base that you were starting with. You know? And a lot of times they won't actually tell you that in the question.
I thought the acids they give away.
They do. That's acids. The conjugate acid comes from a base, which means the base will actually accept it, and the conjugate acid actually will have one more H plus than it started with, because of that. So these are the guys kind of on the right hand side of the arrow as to what you would end up with. All right, so if we look at this again here, just similar to like a question that a lot of times you'll be asked, maybe a little bit more words, but if we want the conjugate acid here and we're starting with this guy, once again, what you want to think about is sort of what it is. So just like we did in this problem, this is where we want to end up. We want to end up with the formula of the conjugate acid. So again, if we go backwards here, what we are actually looking at in this case at the beginning is this guy is going to act as a base. And again, the definition of a base is it will accept an H plus. So in this case, we would actually put on the H plus. The +1 and -1 gives us to neutral, no charge overall, and we have an extra hydrogen in that case. Now, if we wanted to start, so we want a plus and H plus here. If we wanted to do the conjugate base, again, you can follow the same idea. I know the conjugate base is over here, and if I follow this all the way back, that means in this particular case, the HCO3 minus is going to actually act as an acid. And now we could use the definition of Bronsted-Lowry, which is the acid will donate an H plus. So in this case, we actually want to get rid of the H plus. So going in this direction, we want to get rid of that H plus. And that will leave us a CO3. And when we lose the plus, we become one more negative. So already was -1. So we end up with carbonate in this particular case here, CO3. 2 minus. So sometimes it's good to kind of think backwards as to what it is, and all you have to do is kind of go by the Bronsted-Lowry definition of an acid or base, and that will give you the appropriate conjugate acid or base depending on sort of what you're looking at. Clearly in this case, this is another example of one of those guys that are amphoteric, has the ability to act as an acid or base, and typically speaking, those that have like a hydrogen and like a negative sign oftentimes have the ability to kind of go both ways, could act as an acid or base because they have the hydrogen to give. And they also, because they have the negative there, have room for the hydrogen to come in and they can accept it. So they can oftentimes go that way. So something like HCO3 minus, HSO4 minus, you know, these are things that can kind of do both things. Any questions on conjugate acid bases? You know? And remember that the Bronsted-Lowry definition of an acid and base is for these guys, not the conjugate partners. They're just the acid and base. Those are the definitions of those things. All right, so next thing we're going to talk about is the acid-base properties of water. Water is another amphoteric substance. As we saw earlier, water in one case, for example, acted as an acid, which gave away an H+. Water also acted as a base, which accepted the H+. Water could also just react with itself, where one water is an acid and one water is a base. That is sometimes referred to as the autoionization of water. So for example, if one gives away the hydrogen and one accepts it, that is going to form H3O plus and OH minus. It's actually a equilibrium reaction that occurs when water sort of reacts with water. And because it's an equilibrium reaction, we could write an equilibrium constant for it. And we could write our equilibrium constant like normal, which is H plus OH minus. Here, we would not do any of the reactant as it is a liquid, so that would not be included. And as we'll see on the next slide, I think this is what is known as Kw, which is the ionization constant for water. We could add that to our growing list of K values. And again, here we have our acid and conjugate base pair and our base and conjugate acid that's happening here. Now, because of that, we can write our Kw, and our Kw does allow us to calculate a couple of things. Kw, which is equal to H plus times the OH minus concentration, that equals 1 times 10 to the minus 14. And remember that, as I mentioned before, you can swap out my H plus there for H3O plus if you like better. That also equals 1 times 10 to the minus 14. So again, it is interchangeable in formulas and also equations as well. So the brackets again means concentration. So that is usually molarity, right? Moles per liter is what we're talking about there. And it is an equilibrium constant, which means it really does change with temperature, like all equilibrium constants. But I would say 99.99% of the time, if you need to use the value of Kw, 1 times 10 to the minus 14 is the value. If it actually is not 25 degrees and it specifically says it's not 25 degrees, I would say in most book type problems, they'll give you like the value for Kw at that temperature. So it does technically change. Otherwise, it's pretty safe to just assume that's going to be that number. But just a reminder, it is an equilibrium constant value, which means it is affected by temperature. But this is as close to a constant value that we pretty much have for it that we use. Now, what does this allow us to do? Well, again, basically, you could think of the H plus as the acid part of the solution and the OH minus as the base part of the solution. And the relationship between those two things is as the concentration of H plus increases, the concentration of OH minus goes down. So as one goes up, the other goes down. So they are sort of affected by each other. Again, one goes down, the other will go up. And you could actually calculate the value of H plus or OH minus, and depending on the concentration of either the acid part or the base part, it will allow you to know whether or not the solution is acidic, basic, or neutral. If you calculate the H plus concentration and it actually equals the OH minus concentration, that basically means you got 1 times 10 to the minus 7 molar. You will have a neutral solution. If you calculate the H plus and it's larger than the OH minus, so the acid part of the solution is greater than the base part of the solution, then you're going to have an acidic solution. And if you calculate the OH minus and it's larger than the H plus, so the base part of the solution is larger than the H plus, you will have a basic solution. You can basically, the good news is it's the same calculation regardless of which one you're given. You basically just take the H plus time is equal to 1 times 10 to the minus 14 divided by the OH minus, or you could flip it around and kind of do it the opposite way there. The OH minus is equal to 1 times 10 to the minus 14 divided by the H plus. So the good news is it is the same calculation regardless of which one you're given. The key is, again, you would definitely want to make sure you're using your exponent button, obviously, when you punch this in, and then you punch it in correctly. Any questions on that there? All right, so when we try it there, what is the concentration of hydroxide in an HCl solution if the hydrogen ion concentration is 1.3 molar? All right, so here we would use Kw is our H plus concentration, OH minus concentration equals 1 times 10 to the minus 14. In this case, we're given the hydrogen ion concentration of 1.3. So we could rearrange this. And again, like I said a second ago, it pretty much is the same calculation regardless of which one you're given. You're going to take the KW value there and divide it by what was given. And that should get you a number, maybe. We'll go 7.7 times 10 to the minus 15 molar. And obviously in this case here, this would be acidic as the H plus concentration is much larger, obviously, than the OH minus concentration. In this case, when we compare this number to this number, definitely much larger. And we would expect that since this is an acid, so that would be a good idea. Would be acidic, right, in this case. Any questions on that one? Yeah. It probably would be given to you, but it's a number that you use a lot, so it's probably a good number to know, but it probably will be somewhere. But it's one of those numbers you probably use enough that you'll just kind of know it. You know, it's kind of like Avogadro's number. You kind of use it a lot, and you got to just remember it. Yeah. But it probably would be provided to you, I think so. Other question? All right, so why don't you give this one a go? In a solution, the H plus concentration is 1.2 times 10 to the minus 6. What is the OH minus, and is it acidic, basic, or neutral here? Okay, so again here, we'll use our KW, and in this case, we're looking for the hydroxide, so we'll solve for that. Hydroxide, again, going to equal 1 times 10 to the minus 14 divided by our H plus. In this case, we got 1.2, it looks like, times 10 to the minus 6. Again, putting that into our calculator will give you 8.3 times 10 to the minus 9 molar. Or if you're not in scientific notation, a bunch of zeros, about 8 of them, and then a 8 at the end of it, actually. And again, if you're in scientific notation, you get the 8.3 times 10 to the minus 9. That is our OH minus concentration. So in this case, we do want to compare the H plus concentration, which is right here, to the OH minus concentration. And in this particular case, it is the H plus concentration that is larger, right? And that would mean that this is an acidic solution. So maybe there. A reminder that when you compare 10 to the minus 6 versus 10 to the minus 9, when you have a negative exponent, the smaller number is actually the larger number, right? And that's because this is only 6 places that way to put zeros, right? This guy is 9 places that way and putting zeros, which makes it a much smaller number, right? So when you do have a negative exponent, you're comparing the smaller the negative exponent, the larger the number is. Any questions on that there? All right. Any questions on KW there? All right, the next sort of measure of acidity is pH, and pH is a lot of times what we do look at in terms of is something acidic or not. The pH scale runs from 0 to 7 to 14. Below 7 to 0 is acidic. Above 7 to 14 is basic. And dead on 7 is actually neutral. Yeah. Now, 7 sort of your middle point, if you will. As you go from 7 towards 14, you're becoming more basic. As you go from 7 to 0, you're becoming more acidic. And to calculate the pH, we use the formula. I just put a line through there. So that is the pH is equal to negative log of the H plus concentration. Once again, much like a lot of the equations in this chapter, You can go with H3O plus if you like instead. It's, again, basically the same thing. So whichever way you want to do it. Now, when you punch this formula into your calculator and some other ones in this chapter, you do want to make sure that you do punch it in correctly. So depending on the type of calculator you have, if you have a display calculator, you would punch in the negative button, not the subtract button. You would hit the log button, and then you would put your number in, probably using your exponent button, yeah? If you have a non-display calculator, this formula and all the others we're going to kind of see in this chapter, you need to work backwards, which means you need to go with the number, again, probably using your exponent button. You then need to hit the log button, and then you need to hit the negative button, again, not the subtract button on your calculator. If you're not sure what type of calculator you have, just hit the log button. And if it says log on your screen, congratulations, you have a display calculator. If you hit log and it says error, congratulations, you have a non-display calculator. So that's the quickest way to figure out which one you have. So again, if you hit log button and it says log, do it just the way it's written. You hit the log button, it says error, you got to work backwards and start with the number in these calculations to make sure you punch it in correctly. Any questions on that there? All right. So we are going to go with, again, neutral as 7. And that's really because, as I mentioned before there, if they are equal to each other, the H plus OH minus, that is what neutral means. That means you have a H plus concentration of 1 times 10 to the minus 7, which actually gives you a pH of 7 is technically what it is. If you have less than 7, then you're going to be acidic. That also means, just like we saw previously, you will have more H plus in the solution than you do OH minus, and vice versa. If you're above 7, you'll be basic, and you'll have more OH minus in the solution than you do H plus in the solution, so more base than acid. The pH increases as the H plus concentration decreases, and that's also because the OH minus concentration will go up. And also, the opposite is true. The pH will go down as the H plus concentration goes up and the OH minus concentration goes down. So again, everybody kind of working opposites of each other in this particular case. Let's talk a little bit about sig figs and pH type values. The sig figs rule with pH is the number of significant figures in the concentration value is how many decimal places you should have in the pH value. So for example, if I had the H plus concentration of 1 times 10 to the minus 5 molar, what is the correct pH there? Here will equal negative log of 1 times 10 to the minus 5. And on your display, you probably got a 5, hopefully, sitting there staring at you at this point. In terms of the answer here, should the answer be 5.0? Should it be 5? Should it be 5.00? 5.0000? Which one should be the right way to give the answer? We'll start with this one. Is this the right one to give the answer for? The answer is no. How about this one? Answer is still no. This one? The answer is yes. This is the right one right here. This one, too many zeros. That's not right here. Yeah. It works the same way. So you just work it backwards. So let's first talk about this one. So here, when we look at the original concentration value, it has 2 significant figures, right? So it's got 2 sig figs right there. Again, when we're doing concentration to pH type of value, we're going from significant figures, not to significant figures, but to decimal places. So it should have 2 decimal places in this case. Yeah. If you had 5 sig figs, you would go 5 decimal places. Yeah, I guess so. Now to answer your question, when we go backwards, for example, if we're starting with a pH of 5.00 and we wanted the H plus concentration, works the same way. The number of decimal places would give us two significant figures when we go backwards. So works the same way, kind of going back and forth. It's sig figs to decimals, or if you're going back to concentration, decimals to sig figs, basically. Yeah. Other questions? By the way, that would be acidic, basic, neutral. That should be acidic, a pH of 5, less than 7. By the way, when you are asked that question, is it acidic, basic, or neutral? There's just one answer. But some people like to give like it's acidic and it's basic as well. I never had anybody give all three, but I've had people give acidic and basic for the same solution because going could be one of those answers, by the way. We'll talk in right a second here why people do that, but let's talk about a couple of things here. First off, here's the pH scale, as you can see. And we have some pure water there at 7. We got a strong base there at pH 14, strong acid, pH 1, some acids there, some cleaners there. They're basic. By the way, if you take pure water, or if you just take water and leave it out for a while, will the pH be 7? It will not. It'll probably be more acidic in this area. And that's because as it's sitting around, it picks up a little CO2 from the air, makes a little carbonic acid, increases the H plus of it, and it actually will lower the pH in that particular case. Which is why not such a problem these days, because new buildings are built a lot, but old buildings, people used to, before they did something like titration experiment, you did like a 200A. They would boil the water to get rid of the CO2 and bring the pH back up to more of a neutral when you would make something like your sodium hydroxide solution that you made and stuff like that. Now, this is a pH meter, which is a very common sort of thing invented there to figure out the pH of a solution. It's an electrode. You basically calibrate the pH meter and it kind of works through voltages, most of them, and it makes like a little calibration curve. And then you put in your solution and go, okay, that is now a voltage of this, which corresponds to a pH of this, and it spits it out for you. There's also a pH paper, like if you ever did a pool, right? You kind of put it in there, you kind of match up the color, trying to figure out what the pH is. We also have litmus paper, which again doesn't really give you the pH, but it will tell you if it's acidic or basic. Again, red pretty much on litmus paper means acidic, and blue means basic on it. Now, there are similar scales to pH that we sometimes come across, and that, for example, is the pOH. The pOH equals minus the log of the OH minus concentration. The names kind of tell you what you need. So pH, as we just saw earlier, you need the H plus concentration. pOH, you need the OH minus concentration to do that. Why would you want to calculate the pOH? Because there's a really nice relationship between the two, which is if you take the pH plus the pOH, it will equal 14, which means, for example, if you know the OH minus concentration, and you want the pH, all you have to do is get the pOH, subtract 14, and now you have the pH pretty quickly to get there. You can, we'll add our KW here to our list here. Now, we can also, if we are given the pH, so if we're given the pH, we could get directly from the pH the H plus concentration, and that is the inverse log of the minus pH. Yeah. That's the inverse log of the minus pH. On most people's calculator, when they hit the inverse log, it will pop up a 10 and a caret, or how some people do scientific notation incorrectly on their calculator, but this is really what you want to use it for. You want to hit the negative button pH. And you could also, from the pOH, directly get from that the OH minus concentration. It's the same calculation. Inverse log of the minus pOH. Again, a 10 and a caret minus pOH. Also on most people's calculators, to get their top left button, second or shift on the top left corner. And above your log button, it should say like 10 to the X on most people's calculators. And same thing, if you have a display calculator, you could go shift log negative pH. If you have a non-display calculator, you actually have to go pH number first, make it negative, and then hit shift log. Okay, so you got to kind of work backwards in that formula. Um, so this does give you a variety of ways that you can calculate some of this stuff. You may not even need to use KW. You could just use the inverse log if you want. You could still use KW if you want. They all should give you the same answer. So it's just kind of your preference as to which way you go. Now, I said a second ago that sometimes people give more than one answer for, is it acidic, basic, or neutral? And the reason for that is these two guys right here. They calculate the pH and go, cool, it's above 7, it's basic. Then for the same solution, they calculate the pOH and they go, cool, it's below 7, it's acidic. And now the same solution is both acidic and basic at the same time. Should not be. My highly recommendation is always look at the pH value because that is the scale most people have in their head. The pOH actually runs opposite of the pH scale, which means if you have the pH scale, that's 0, 7, 14. That's basic, that's acidic, and obviously that's neutral. If you have the pOH scale, it also goes 0, 7, 14. Difference is that's acidic, that's basic, and that is neutral. So if you have a low pH, less than 7, you'll have a higher pOH, obviously, and vice versa and stuff like that. So it is opposite. And since most people don't have this scale in their head, most people have this scale in their head, you should always probably look at the pH value. And again, just give one answer for that question that you're asked. Any questions? All right, so let's try some here. We have rainwater and the pH there is 4.82. Let's just calculate everything, make sure our calculators work. So we want to know what is the H plus concentration, what is the OH minus concentration, what is the pOH, and is it acidic, basic, or neutral? And for the bottom one, let's calculate the pH, the pOH, the H plus concentration, and is it acidic, basic, or neutral? All right, so take a few moments there and calculate each of those and see what you come up with. Okay, let's take a look, see how you're doing. So since we're looking for everything, do you have some options as to where to start first? In the first one, we are given the pH. So from that, we could get to H plus concentration. We could also get to the pOH, so it doesn't really matter here. So what I'm going to do, I'm going to go pOH first. Why not? So the pOH would be 14 minus the pH, which would give me 14 minus 4.82 in this case. That's going to be 14, 4.82, 9.18 as our pOH. At this point, I do have the pH and the pOH. I can get the H plus directly from that. Once again, I'm going to go H plus is equal to the inverse log of the negative pH. Don't forget the negative there. Again, when you punch it on your calculator, it should probably look something like this, I would imagine. Once you do that, hit the shift log and kind of do that move. Minus 4.82. It's going to give us a 1.5 times 10 to the minus 5. This does need molarity as it is a concentration. Now that I do have the H plus, I still have really two options as to how I could get to the OH minus. I could definitely use KW like we did previously and do 1 times 10 to the minus 14 divide it. I could also do, since I do have the pOH, the same calculation to get to the OH minus. So I'll do that one the same way. So I'll go the OH minus will equal the inverse log of the minus pOH. That's going to give me a 10 and a caret minus 9.18. Alternatively, you could have done the OH minus is equal to 1 times 10 to the minus 14 divided by 1.5 times 10 to the minus 5. They both really should kind of get you to the same spot, regardless of sort of which way you want to go. Maybe slightly off depending on where you rounded, but should be pretty close. So We'll go 6.6 times 10 to the minus 10 molar would be our OH minus concentration. At this point, the last thing we're looking for is it acidic, basic, or neutral. Once again, we always want to look at the pH value, and that is less than 7. So it is acidic. Any questions on any of those there? By the way, going backwards, as was the question, 2 decimal places gives me 2 significant figures, kind of going backwards. Yeah, so 2 to 2 there. Yeah, in that case. Any questions on any of those there? All right, bottom one here, we got going here. We are given the OH minus concentration. So again, it does open up a few doors for us since we're looking to solve for everything. We could just go right into the POH if we like, minus the log of 2.5 times 10 to the minus 7. And that's going to get us minus a log here, 2.5 to the minus 7. Looks like a 6.60. I could very easily now get the pH from that by simply just taking 14 minus the POH. So super easy to get to the pH at that point. It's gonna be a 7.40. And lastly, H plus. So again, since I do have the pH, I could do the inverse log of it. I could still do the KW. So I'll go that route on this one, minus 14 divided by 2.5 times 10 to the minus 7. So we'll go 1 to the minus 14 divided by 2.5 to the minus 7. Looks like 4.0 times 10 to the minus 8 molar would be our choice. Again, looking at the pH, slightly above 7 there. So it's going to be slightly basic. Yeah. Let's get any questions on any of those there? POH to pH, so yes. Yeah. So, and that comes from that relationship we saw, which is the pH plus the POH equals 14. And that means that if you have either the pH or the POH value, to get the other one, all you have to do is take 14 minus whichever one you have, and it'll give you the other guy, basically. Yeah. Other questions? All right, question on calculate any of that there. You do need to be able to obviously calculate any of those things along the way. Let's try one more here just to make sure. Looking for everything, and we'll add is it acidic, basic, or neutral here. All right, let's take a look. Again, we're given the H plus, so it does give us a couple of options since we're looking for everything. We again could go KW route to get the OH minus first. We could also just go right into the pH as well. So that's what I think I'm going to do, just go straight into the pH. But you definitely could have went the KW route first if you wanted to. 3.5 times 10 to the minus 6 in this case. That's going to get you minus negative, there it is, log 3.5 to the minus 6. I'll get you a 5.46 on the pH. Clearly, the easy thing to get next would be the, I put the right letter there, POH minus, come here, 14 minus the pH. So 14 minus 5.46 in this case. So minus 14, 854 looks like. What's left there? OH minus. So again, you could still KW. You could, now that you have the POH, do the inverse log. So we'll try that one. Inverse log of the negative POH. Again, on your calculator, probably should look something like this. And that's going to get us here. It's like a 2.9 times 10 to the minus 9 molar as well. And in this case, again, we want to look at the pH value, which is less than 7. So it is acidic in this case. Yeah. Questions on any of those there? And again, like I said, there's some different routes that you could take, but they really should give you the same answer depending on no matter which kind of way you went there. All right, so let's talk a little about electrolytes and acids and bases. So first off, strong electrolytes. Electrolytes, as you may remember, are substances that break apart into ions in solution. The presence of those ions helps it conduct electricity. A strong electrolyte is something that will 100% break apart in solution. It will not stay together. So if you had sodium chloride in water, basically a sodium chloride solution, it will 100% in that solution basically just have those ions floating around. So you would just have sodium ions floating around and chloride ions floating around. You would have none of these sort of sodium chloride units still together. It's just going to completely basically fall apart, hence the one-way direction of the arrow. Everybody's just going to dump out there on the product side. Weak electrolytes, on the other hand, are not completely dissociated. Weak electrolytes mainly stay together, but they do break apart a little bit. So in this case, you would break apart acetic acid here into acetate and H plus, and you would have a little of these guys in solution, and you would mainly have kind of the whole thing still together. So if you kind of looked at a solution of that, you would mainly have this whole thing together, and just a little bit of the ions that are floating around in that solution. Now, when we talk about electrolytes, strong and weak, they represent also acids and bases can be strong or weak. And with a weak electrolyte or a weak acid or base, again, we get the reversible reaction that's going to happen. It's going to set up an equilibrium, where obviously something that's strong will not. Strong acids, there's a bunch of strong acids that you really should know. It just makes life easier. And the list is pretty much what we have on the bottom there. We have hydrochloric acid, nitric acid, um, perchloric acid, sulfuric acid, hydrobromic acid, and hydriodic acid. This list of 6 strong acids are really good ones to know, because it allows you really to do a couple of things that's sort of important for you. If it is not one of those 6, then you could probably safely assume it's going to be a weak acid. So it's because by process of elimination, it's much easier just to know these 6 rather than all the acids, right? So if you know these 6 are strong and it's not one of the 6, probably a safe bet you're dealing with something that's weak in terms of an acid. Um, Now, most weak acids are weak electrolytes. So, those are things like HF, acetic acid. Because of that, they will 100% break apart here into the ions. So you'll get H3O plus and Cl minus. Again, with our H plus coming this way, H3O plus and NO3 minus, H3O plus and ClO4 minus, and H3O plus plus HSO4 minus, basically in this case. So these are all, again, strong acids. They should all completely dissociate in solution. Now, we do have weak acids, and as I mentioned before, these are some common weak acids. HF, acetic acid, is also a very common weak acid, as well. These guys will, again, mainly stay together, so it will still break apart into some ions. So get H3O plus and F minus, H3O plus and NO2 minus, H3O plus and SO4 2 minus, and obviously our H3O plus and our hydroxide here in this particular case. Now, in terms of strong bases, much like strong acids or strong electrolytes, they do 100% break apart. So something like sodium hydroxide, you're gonna get 100% ions presence, potassium hydroxide, 100% ions as well. That is why, again, they are strong bases because all they have to do is go for a swim. They're going to produce OH minus in that solution pretty quickly. You're going to now have a lot of OH minus freely floating in that solution, and that's why they're considered, again, a strong base. Just like when we talked about our acids, they're going to completely break apart, which again is going to influx a lot of H plus into that solution really, really quickly. And that's why they're considered strong acids. These guys, again, are going to mainly stay together. So if you had a beaker of HF, you would mainly have the HF guys still together, but will produce a few ions. So since it's able to produce a few ions, it's still considered an acid, but it would produce nowhere near the amount, for example, of like hydrochloric acid that went into that solution. That's going to just fall apart completely. Same thing here with our hydroxide or sodium hydroxide. When you do that, you're just going to produce a bunch of sodium ions, but more importantly for like pH and all that, you are going to produce a bunch of free OH minuses in that solution. And that's going to create obviously a more basic sort of situation. Once again, on the periodic table, if you hit lithium, you hit sodium, you hit potassium, make a right-hand turn to calcium, strontium, and barium. Any of these guys in group 1 or group 2 that have hydroxide in the actual formula are typically your strong bases. So that's where you find a lot of your strong bases we talked about last time. Group 1 or group 2 on the periodic table, definitely going to be more of a strong base situation happening. We also have some weak bases, and weak bases will mainly stay together but can produce, and they will basically accept the H plus coming in this direction, and it will produce actually where they come from in terms of the acid. And more importantly, it will produce hydroxide, which is why they're considered a base, because they will produce that hydroxide. And here you'll get HNO2 and some hydroxide as well produced in this particular case. Now, there is a really important relationship between sort of acids and bases and their conjugate partners. And it's a really important thing to remember when we look a little later on this chapter and some other chapters. And that relationship is this. If you have an acid, its partner will be on the other side, the conjugate base. And if your acid is a strong acid, its conjugate partner will be considered relatively weak. So sort of an opposite relationship there. If your acid is actually a weak acid, your conjugate base will be considered a relatively strong conjugate base. Now, same thing will happen for our base and conjugate acid type of situation. If you have a strong base, your conjugate acid is going to be relatively weak. And if you have a weak base, it will be relatively strong in this case. So what are we talking about when we talk about kind of strong in this situation? Just so you understand, it'll probably become clearer later on as well. When we talk about strong in this situation, it is not as strong as like a strong acid or a strong base. What it means and what we'll talk about is there are certain conjugate partners, like conjugate bases or conjugate acids, that once they are produced in solution, they have the ability to continue on and react with water. And that is what we have with these guys. These guys that are strong, that say conjugate base can react with water. And what's going to happen, for example, if the conjugate base does react with water is it's going to act as a base, which means it will accept an H plus from water. And what will happen is ultimately you will produce hydroxide as a result of that reaction happening. And because hydroxide can be produced in this case, it will affect the pH of that solution. We would expect it to be more basic because now we have this conjugate base kind of still reacting with water at this point and producing more OH minus and going to make that solution more basic. Same thing could happen. You could have a conjugate acid that can react with water. And in this case, it will act as an acid and donate an H plus over. The result of that is this guy would actually make some H3O plus, and this solution would actually become more acidic because of that reaction. So as like a side reaction that could happen in a reaction of an acid and a base, you could get these things, as we'll talk about a little later on, which are known as salts, that can continue to react with water and have an effect on the pH of that solution. These type of reactions where we react with water is sometimes referred to as hydrolysis reactions, which means it's reacting with water. And we're going to talk all about what's going to happen with that in a bit. But again, the idea here at this point is when we talk about it being a relatively strong conjugate base, it's not like a strong base or anything like that. Something like sodium hydroxide is way stronger. Or a strong conjugate acid, something like hydrochloric acid, is way stronger than those guys. But it's strong in the sense that it has the ability to continue to react with water, is what we're kind of talking about. Things that are considered weak conjugate bases or weak conjugate acids, they pretty much will sit there and not react with water. So they're kind of thought of as being more like a neutral type of salt, and they won't react with water in that case. Any questions on that there? So yeah. Yeah, so the sort of relationship between that is if you have something weak, what it will produce is something that when it's in the presence of water, which is what all these things are, because it's an aqueous solution, there's always water present. It's strong enough that it will be attracted to the water and there'll be some interaction that's going to happen. In the case of something that's weak, that will be there still with the water, but there's really no incentive or attraction of those things starting to react. So it's just a process of those two things when they're kind of near each other will want to actually continue on and do kind of another like acid base reaction where something that's weak will not. So for example, you had something like Na plus, for example, that comes from like sodium hydroxide. Na plus will just float around. It's not going to really interact with water and do much with it at all. But you know, if you had something, for example, like this guy here, this guy, it's got a minus charge and it's willing to sort of accept that H plus, so it's going to interact well, much better with water in that particular situation. So this is a table, you have a similar in your book, again, of some strong acids and strong bases. And again, that opposite relationship of their partners, either going to be stronger or weak, depending on where it comes from. Again, with a strong acid, we expect complete dissociation. So in a solution of hydrochloric acid, we would expect all of that to be present. Again, when hydrofluoric acid, which is weak, we'd actually expect a lot more of the intact acid still to be there, and the ions that are out there just kind of floating around. So if we have, for example, something like hydrochloric acid, which is a strong acid, and it broke apart into H plus and Cl minus. And let's just say we had, in terms of hydrochloric acid, a concentration of 0.1 molar, right? If we were interested in the pH of the hydrochloric acid, the important thing for pH is negative log of the H plus concentration. So we would want to know the concentration of H plus in this case to allow us to calculate it. And as you may remember when you talked about solutions of molarity, I hope, this is a 1-to-1 relationship between those two, which means the concentration of H plus in this case would be 0.1 as well. Concentration of Cl minus, also a 1-to-1 relationship, would also be 0.1 as well. Not that we need it in this case. So by knowing the strong acid here, we basically know the H plus concentration, and we could actually put it into our pH there equation and get our pH of 1 in this case, and be 1.0 in this case as one significant figure. Now, if you're not sure what I'm talking about, I'll just do the long version of that calculation, which is 0.1 moles per liter of HCl. You basically are doing a mole to mole relationship, right? It is a 1 mole of HCl gives you 1 mole of H plus. Moles of HCl cancel, and you end up with 0.1 moles per liter of H plus. So the quick way to do it is obviously whatever it breaks apart into, you multiply the concentration by the coefficient. So if it's a 1-to-1, you get the same concentration. If it breaks apart into a 1-to-3, you get multiply the concentration by 3 for the ion. That's the quick way of doing that. Same thing with sodium hydroxide, for example. Let's say we had a 0.1 molar sodium hydroxide solution. Because that is a strong base, it would break apart into Na plus and OH minus. In this case, the important thing for pH is actually the OH minus here. This would allow us to get to the POH. And we would do the same thing. It's a 1-to-1 relationship, which means the concentration of OH minus in this case would be 0.1. That means my POH would be minus the log of 0.1, which would give me a POH of 1. That is, again, not the pH, right? Because this should actually be basic. So the pH here would be 14 minus 1 or 13, which definitely is basic and would make sense in this case. So you could do it for a strong acid or strong base. You could calculate the pH. Sometimes they don't just give you like the generic H plus or OH minus. They may actually give you a formula, and if that formula is a strong acid, the good news is most of the strong acids are monoprotic, which means if you know the concentration of the strong acid, you know the concentration of the H plus, you could just go right in to the pH equation. For a base, if it's something with hydroxide, it most likely is going to be a strong base. So you would need to get the hydroxide concentration, get the POH, subtract 14, and get to the pH. So sometimes they may actually give you a formula for an acid or base rather than just generically the H plus, H3O plus, or OH minus concentration. Any questions on that there? All right, so why don't you try that there for each of these? What is the pH of each? Okay, so let's take a look. So again, we have nitric acid here. That is one of those kind of 6 strong acids that was on that little list. So again, I know this is going to be a strong acid. So I do know that when it is in solution, it's going to 100% break apart into H plus and NO3 minus. And because of that, again, it's going to be our H plus that we're interested in. And it is a 1-to-1 relationship, which means the concentration of the H plus would also be 2 times 10 to the minus 3 molar, basically 1 times that value, which gives you the same value. It also would be the same for the nitrate, but not really necessary in this question. The pH then would be negative log of our H plus, and that's going to get us negative log of 2 times 10 to the minus 3. And looks like a 2.7 in this case, which is acidic and makes sense since that is an acid. So again, if you by some chance got a basic pH here, that would definitely not make sense. Yeah, you definitely punched something in incorrect. First off, any questions on that one there? Next one is barium hydroxide, which is like OH and one of those group 1 or 2, so probably a strong base. So that is barium hydroxide, and because it's a strong base, it's going to break apart into a barium ion, and we will get 2 hydroxide ions here. In this case. And in this case, it is the OH minus is of interest so that we could get probably to our POH and then to our pH in terms of our root there. This is 1.8 times 10 to the minus 2 molar. It is a 1-to-2 relationship here. So we do actually have to multiply the concentration of hydroxide by 2 to get the correct concentration. And if you do that there, 1.8 to the minus 2 times 2, going to give you a 3.6 times 10 to the minus 2 molar. That is our correct hydroxide concentration. So that will go into our POH, which would be minus the log of the OH minus. minus log of 3.6 to the minus 2. And at this point, then we would do a little bit of that, and we will get a 1.44. Again, at this point, if for some reason you thought that was the pH, it really shouldn't make sense to you, right? Because that would then be an acidic pH, and this is a base. So again, those things don't make sense. We do need to get to our pH by taking 14 minus our POH, and that'll give us 14 minus 1.44, looking like a 1256, it looks like. And a 1256 is definitely basic, which again does make sense in this case. Any questions on those two there? So again, if you're given something that's strong, either acid or base, pretty much just need to get the H plus or OH minus to get yourself to the pH of the solution. Again, just another table here. There's our 6 strong acids and really kind of our 6 strong bases from our group 1 and group 2. Again, hanging it right there at potassium, then coming down on the group 2. All right, any questions on any of that? It's probably good